Thank you very much, and good afternoon to everyone. So this is some work I've been, well, part of it has been going on for a number of years now, but the machine learning part has been developing over the last couple of years, especially with my very good friends, Fivos Diakogiannis, Benoît Famé, and Giacomo Monari. The last two here in Strasbourg, and Fivos is in Perth. So what I want to talk to you about today, if this works, is essentially give you a very quick overview about the astrophysical motivation before going into some detail into the machine learning on dynamics that what we've been up to. So I want to tell you about stellar streams and how we're using these to try and constrain the dark matter. And the basic idea behind all of this, right, is that all these theories of gravity that are competing with each other to, what they actually do is predict accelerations. But in the region, in the regime where they actually have any differences, which is the weak field regime, they're very hard to measure. I mean, the accelerations themselves are very hard to measure, right? So it's difficult to bring this information to bear on the theories to try and discriminate between them. And so typically, of course, what we do in astrophysics is try and figure out the equilibrium of a galaxy and try and understand that with, for instance, like the genes analysis. But as we know already from the Milky Way, the Milky Way is not an equilibrium structure, as we see in this this spirally pattern here of the local velocities around the sun. So, an alternative would be to wait for millions of years for the stars to actually, change in their motions for their velocities to change over time. But again, this takes a very long time, and obviously that would be extremely boring. So another opportunity we have to try and constrain this is by using the continuity of structures. And this is where stellar streams come in handy, because they have this sort of natural continuity, right? So, of course, if we had, over a period of time, here I'm just showing, the passage of some star through a galaxy over time. And if we had the sort of information that I'm showing here, so, the positions and velocities over time, we would trivially be able to get the underlying acceleration field. Now, what we're trying to do is to use streams as a means to get this sort of information, because as the mass of a stream progenitor gets very small, effectively a stellar stream starts to look like an orbit on the sky. And even though this isn't precisely true, we know how to run n-body simulations to essentially correct back to get the orbit in the first place. So this is the idea behind this. And these stellar streams have lots of other very handy properties as well. They allow us to get this acceleration field that we're after. You don't need to assume equilibrium dynamics, because in fact, this is one of the really nice things about them. They retain this memory of the interactions that they might have had in the past, including with, for instance, CDM subhalos. So you can gaps that may form. You may find bleeding of the stellar streams. The bar satellites or the disk of the Milky Way can all leave imprints on these streams that we can then go in and find, because many of them are really very cold and really very fine structures. And so this is also allowing us to trace how the galaxy has built up over time. So these are the really nice properties of stellar streams. And this is partially the reason why people have been hunting for these structures now for going on 20 years or so, if not much longer, actually. And a huge advance was made with the Sloan Digital Sky Survey. You can see here that these two very large branches of the Sagittarius galaxy that's seen going straight through the North Galactic Cap, but you can see many other little structures all over the place. And these probe then structures all the way from pretty close by out into the outer regions of the halo. Further photometric surveys such as Pan-STARRS and Deep Energy Survey, started showing up many more. But really, it was, we've now had a huge leap ahead thanks to Gaia, because with Gaia we have the proper motions, in some cases the parallaxes of the stars, and this gives a hugely richer data set to play around with. And so what we were doing over the past couple of years is trying to develop a method to actually find these streams. And I won't go into this in any detail other to show that it actually works. Essentially, as a sort of friend of friend finder in sort of 6-dimensional space. And this has allowed us to find a huge number of streams through the Milky Way. This is the final result of our search on Gaia DR2, the data release 2 data set. And you can see these various streams that go through the galaxy, and here this is in galactic longitude versus latitude, and the color coded according to the proper motion in the galactic longitude direction and the galactic latitude direction here. So you see these structures have beautiful kinematic coherence, very clear on the sky. And we went and followed up these structures also with high resolution spectrographs, so Espadon at the CFHC and UVIS at ESO, and they have also, so these essentially is confirmation of these structures. They have beautiful line of sight kinematic coherence as well. More recently, then the Gaia EDR3 dataset came out in December. And we were able to run exactly the same software through this. And as of an hour and a half ago, I have the very, very latest reductions that we made with this software that we found, that we've developed. And so, the galaxy is a hugely streamy place. And again, this shows you the same view of the sky, color-coded by the galactic longitude component of proper motion in the range between 3 and 12 kiloparsecs, so the sort of closest streams to us. And then the same thing again as of an hour and a half ago. This is what it looks like in the range between 10 and 30 kiloparsecs, so a little bit further away. And you see this. This is actually the Sagittarius stream that we saw in one of the earlier plots, but lots and lots of other structures going on here. And many of them are really exciting. There's some structures that we've been able to follow up with high resolution spectroscopy, and actually one of them is the lowest metallicity system yet known. So there's lots of astrophysics to be done here, as well as trying to understand what the acceleration field of the Milky Way looks like over this vast region of our galaxy. So this is what we're currently doing, sort of building up our, trying to use these streams then to figure out what the acceleration field is doing. And so we're in the process of running in-body simulations for the various streams and then correcting back then to the orbits. And then when all of this is done, we hope to be able to run an MCMC routine to get the acceleration field, and hopefully that'll be perhaps the best measurement of the galactic potential out to something like 30 kiloparsecs that we can get. But in doing this work, we realized pretty early on that one of the things that we have the least control over is the distances to the structures. And so we started thinking, well, how could we improve the distances? And so about a year ago, we began thinking about using the photometry that Gaia gives us alongside UGRIZ photometry from Pan-STARRS or Sloan to try and predict the metallicity, log G, and an effective temperature of the stars. And this is the result of Luana Ramus's master's internship. And we just built a very simple neural network to be able to make this prediction. Essentially, given photometry, we tried to predict what the stellar parameters would be, and we were using ground truth data from Segway and the MOST. And this worked extremely well, as you can see here. For instance, here these are the real values of the metallicity of the stars. And these are the predictions out of the network, and you can see that they work really quite well given the quality of these of the photometry. Likewise for the temperature and for the law of gravity, which essentially allows you then to get a better measurement of on the distances, better constraints on the distances. And so this was very simple to set up. And we've gotten some initial results within a couple of weeks of doing this, and so we were very, very pleased, and it immediately led us to think, oh well, this is really, really very cool, right? Because you can imagine using something like this in all sorts of different ways. So not only can we go from photometry to the stellar parameters, but we could try and go back again, right? And so sort of make an autoencoder that would allow us to essentially translate data from one photometric system or into other photometric systems. You might also wonder, well, is this actually enough? Do we need extra parameters? And in fact, maybe temperature, log G, and FEH aren't actually the most efficient parameter set. Maybe nature likes other things, and so on and so forth. And so we got really very excited with this. And as part of that excitement sort of led into, oh, can we actually use this technology then for dynamics? And this is where it started getting really interesting, I thought. So let's just sort of take a step back and think about the action angle variables, because this is the way that we attack the problem. So what we started off doing was using well, we wanted to approach this problem by thinking about actions and angles of the stellar streams that we were trying to study. And the idea behind this is that the actions and angles are convenient because along an orbit, the actions are conserved, and anything that changes is the angle coordinate theta. So an orbit that looks like an ellipse here in position and velocity then just becomes a straight line in this space. But when you add in the additional, well, we have 3 actions and 3 angles. And what an orbit does in this in this 6-dimensional action angle space is follow the surface of a hypertorus. And so this little plot here is showing you what it would look like if you had 2 actions and 2 angles. And so an orbit would sort of follow some path along this hypertorus. And they're very convenient because they're, the actions are adiabatic invariants. And so they get conserved with during the evolution of the Milky Way if it's not changing all that much. So typically we have in an axisymmetric system, we'll have J phi, which is the same thing as the Z component of angular momentum. And this picture here from Jean-Baptiste Fouvry shows you what happens if this orbit here, if we take this orbit here and we increase the R component of the JR, that means it sort of sloshes out a little bit further in radius, and increasing JZ makes us go further away from the galactic plane. Okay, so these are all very, very nice, but the problem is that these, in almost all dynamical systems that we'd be interested in, it's not easy to calculate these J's and thetas. And there's this well-known machinery that was developed by James Binney and many collaborators over the years called this torus machine, that, you know, when I initially looked at it, it seemed really very complicated, but in fact it's not. And so one of the nice things, I presume everybody here works with well, some variant of the machine learning libraries, but I was able to set up something that did exactly this particular problem in a little less than a morning. With PyTorch. And so the idea behind this, although it may seem complicated, is actually very simple. And it's just that we're trying to go from observed positions and velocities to the angles and the actions of some system, some target system whose potential we know, whose Hamiltonian we know. But this method actually does the opposite of what we might want to do. You start off by guessing an action in the system of interest. You then go and fill out this torus with a mesh in 3 dimensions, because there are three angles, theta, so that you can then apply a generating function that allows you to go from the initial guessed actions using your mesh of toy angles, and that then gives you the toy action. And then finally, you go back from this toy system to real space, to real XV space. Well, I suppose they're all real, but to the original observable positions and velocities, just using the inverse of the toy model. And as I say, this is actually quite easy to set up with PyTorch. And the trick behind all of this is that you use a generating function, and that generating function is described as a Fourier series in this way here. And what James and collaborators have done over the years is to set up Marquardt, Liebenberg minimization routines to try and find the Fourier components of this decomposition. And so this allows you then to, well, it allows you to go from a target system to from actions in a target system to positions and velocities. And so it's kind of a bit annoying, right? Because it goes in the opposite way to the way that you'd actually like to go, because generally you observe X and V's and you'd want to know what their actions are. And the other thing is that you need to know what the Hamiltonian of the system is in advance. So you need to know where what system you're actually dealing with. And for some systems, you might need a very large number of Fourier terms. So you need a lot of data then to constrain this problem. So first of all, we started thinking, well, how could we use deep learning to try and help us with this problem? And yes, you can, right? It's essentially we could just use a deep dense neural network. I'm just taking a plot out of from the internet, so where you would feed in input positions and velocities, and if you know the actions and angles of some system, you could train this network relatively easily. So this is essentially a supervised learning problem. And I say relatively easy because there are some sort of problems, right? And let me just mention that a little bit. The architecture we managed to use to get this looked like the typical neural network with residual dense layers here. So you have some, you put in your XV here and you get out your J theta here at the end. And inside each one of these layers, you have a ReLU, a linear layer, and then some normalization. And you do this twice, and then you put in the input onto the output. And this is actually very, as I'm sure you all know, is a very powerful way of constructing such networks. But I just want to insist on one thing that took me like a month of my time to figure out, which is that generally people use batch norms in these layers here at the end. And so batch norms are really very, very useful. And they've been, in typical applications to images, they're very handy because they allow you to train a very deep network, because as I'm sure you know, what the batch normalization does is to learn the bias and the dispersion of the outputs of each layer, and then this gets learned, and so effectively you take out the dependency of one layer on the next ones down, and so it allows you to train very deep networks. If you didn't have something like this, and I've tried this to getting rid of batch normalization. Essentially, you have a horrible, well, as they call it, this covariate shift, right? So essentially, it's as you train some layer up here, you'll then break the predictions further down. But the bad thing about batch normalization in cases where you have tabular data and you're actually really interested in high precision work is that it's limited by the shot noise of the data in each batch, and so unless you had very large, and I guess maybe when GPUs have sufficient memory on the card, it won't be a problem. But in most cases, you feed a small number of data to each one of these in a batch to each one of these layers, and this ends up giving a huge amount of variation to the normalization. And so essentially, what it doesn't allow you to recover the coordinates that you're after with very high precision at all. I built my own workaround using batch normalization, which I won't go into here. But in fact, in the end, I ended up using this weight norm method, which actually works very much better for tabular data. So if you ever come across this particular problem, I recommend you look into other normalization issues. So basically what this, so when we initially applied this this model, we were able to go directly, as I showed you in this, using a deep network, going from the positions and velocities all the way through to the actions and angles. But it takes an enormous amount of computational effort to do this because of the the very complicated nature of this of the transformation. And we found that that in fact, if we used a toy model as a starting point and built a correction on the toy model, the computational effort could be reduced by enormous factors. And so this would you in this effort of trying to go from positions and velocities to actions and angles in a supervised way, we ended up using this particular architecture here that is shown here. And I think this is actually really very powerful. So if you have a data set that you're trying to model and you have a first approximation to it, then effectively doing a a correction to that spherical cow model allows you to make a very much better model of your data than you would do just with a normal deep neural network. Okay, so yes, so you can go from positions and velocities to actions and angles, but the issue is that most of the time in a supervised way, but most of the time you won't actually know what actions and angles are for in the systems of interest. So in reality, the Milky Way doesn't actually, there aren't stars going around with tags of actions and angles. So so we don't actually have this information to be able to do the training. So how can we get around this? And so let's remember again that what we're doing, the approximation that we're taking, is to assume that that stellar streams approximate orbits on the sky, and that along those orbits, actions remain constant. So how can we get around this? So what we ended up doing was developing an unsupervised network that learned the generating function from the angles of a toy network and the actions of the target system, and that allowed you to go from these then to the positions and velocity. So essentially, the method is sketched here. You start off by having your positions and velocities. You use an analytic isochrone as a toy, and there's an interesting loop inside the algorithm that sort of accounts for the symplectic nature of this generating function transformation, and So at the end of this process, what we obtain then is we're able to go from the initial positions and velocities to the actions and angles at the end, without having used any information about the Hamiltonian or the potential, and we haven't required any symmetry to the problem. Essentially, the magic comes in at this level here through the loss function, which is that essentially what we do is we require the actions for stars along a given stream to be identical. So let me just sort of sketch that out for you. What we have here, we're imagining a couple of streams in our galaxy for which we have positions and velocities. We apply a simple analytic transformation to these to take them from position and velocity into a toy system, actions and angles. Then these are then transformed using this generating function that we learn. In fact, there are two of these. One is it takes us from the actions and angles in the toy system into a new action, closer to real action and angle system, and then finally there's a point transformation as well. And so at the end, what we hope, and this is then fed in, is required by the loss function, is that the spread in the J's here in each one of these different orbits should be as small as possible. And the nice thing about this also is that it immediately gives us what the acceleration field is. Thanks to the automatic differentiation package within PyTorch, we have the derivatives of the actions, and then so immediately we can solve this equation to recover what the accelerations, so what the acceleration field is through the galaxy. So we tried this with a few reasonably realistic Milky Way models. So this is with the Denon and Binney galactic model. Here we're imagining we have 128 streams, each one of these streams with 8 stars. And we are able to recover the true actions with the system to less than 1% accuracy, with essentially just with just about 1,000 data points. So at present, we don't actually have this information, right? Because we don't really have the proper distances, but this is something that we're currently building on. And so the architecture of this system then would look like this. Essentially, we're using the data, using a toy model and a generating function rather than just a correction to the toy model to compare then to our data set. So the things that I'd really like to be thinking about over the next little while, so my next plans are I've been very, very impressed by the power of two ideas that have come out in machine learning, I guess, is one of which are the convolutional neural networks that are used in image analysis. The other ones are these GANs. And I think it would be really nice if one could use, well, the convolutional methods for tabular data, like the ones that we have here. But I really don't have a clue how to do this, and it's been really bothering me because it seems like one should be able to do something like this. And the other one is using GANs for these sort of dynamics problems, and here I'm thinking of perhaps having a system that would propose distribution functions, perhaps, and then having another a discriminator decide whether they're plausible or not, or they can agree with the data. And so this is something that I'd really like to be thinking about over the coming months. So then, just to wrap up, what we've been able to do is to develop an algorithm that is able to approximate this transformation, the canonical transformation between positions and velocities to actions and angles. And currently this is built in such a way that it can work on Gaia type observables, so on proper motions, parallaxes, and positions on the sky. So this is actually is currently built so that, you know, it should be applicable soon to Gaia. And the key advance of this is that we don't actually need to know what the potential or the Hamiltonian is in advance. Yeah, I don't know yet. Well, we don't know yet how the observational uncertainties are going to affect the results that we get. And so, yeah, I'd like to hear over the coming weeks what you're all working on, and hopefully over the coming months we might be able to discuss things in more detail, maybe even develop some collaborations. So this is where I'd like to stop. Thank you very much.
Thank you, Rodrigo. So, is there any question for Rodrigo right now? Does this work, Françoise?
Well, yes, maybe it's very interesting, and maybe magic that you can retrieve that without any Hamiltonian or potential. But still, of course, you have not yet evaluated the uncertainties due to the observational errors and so on. But I think that it would be certainly much better if you use the potential that you already know, because we know the first approximation of the potential in the galaxy.
Yes, yeah, no, it's very true that we do know that. I think we know it in certain places, and we know it. I mean, one of the things that's really struck me is just how well this particular model that dates now back 20 years. I mean, it's been very good in allowing us to actually discover the streams in the first place. And so clearly it can't be very wrong. But at the same time, whenever we look at a particular system, we find that you know, there are always little worries that you know, about the flattening of the potential, the triaxiality, and so on, and even locally, right? I mean, there could be some. I mean, in principle, this method should be completely flexible, given enough data. And I guess we need to go through and actually see what happens when you know, add in a bit of mass in some place in a complicated way, whether the actions, angles, and the acceleration field that we recover are the correct ones.
Yes, because when you say that you will derive the acceleration from J, and the velocities and so on, but then you will get only the very, very local acceleration at each point at each velocity of the orbit. So it could be, if there is, I don't know, a globular cluster there, or an accident of the potential. So you will need to know the large scale potential before interpreting these small scale local accelerations.
Except that these structures are very, you know, many of them cover huge long tracts on the sky, right? So, yeah. For instance, some of these are, you know, close to 200 degrees long on the sky. They're very big structures, and they're all crisscrossing, right? And so what happens here is that, at least, you know, we have, I say immediately, we haven't applied this to real data, right? And on top of it, we don't have. And the tests that I've run on it so far use perfect data. I mean, they use very, very small amounts of data, right? So there's close to 100,000 stars here, for instance, in this particular plot. But the only thing that you know, this particular algorithm required in order to get you know, below 1% on the actions was 1,000 points. So there certainly are the number of stars out there in the galaxy. The only problem is that we don't actually have radial velocities for most of these stars. They're going to come in the coming years, right? And Weave and Foremost are going to give us the radial velocities, and I presume also with you know, with RL-IRIs, we're slowly we're going to be able to really nail down the distances to these structures. And so I think there's good, there's, you know, the prospects are good to actually have the sort of data set that we would require in order to measure the acceleration field. But the point is that, you know, one takes all of this information and the network adapts itself. It builds this generating function that then solves the whole lot in one go, right? And so it's not really a local measure that it makes. It's just that along each one of these structures, it's assuming that the actions are constant, right? So each one of these will be taking a different slice through through action space.
Mhm. Well, it will be interesting to compare the acceleration that you find with the normal potential to see if you're far.
Yes, absolutely.
It is true, if there is a bar or something triaxial or something, the G will not be constant.
Yes, yeah. Yes, and people have said that you know, some of the streams are perhaps affected precisely by the bar, right? And so both things are going to advance in you know, at the same time. I mean, we're doing our M-body modeling using a classical potential, and then figuring out what the corrections between orbits and those M-body models are, and then, you know, as I said in the talk, I mean, one of our aims is to then put the whole thing into a big MCMC and then just sort of get out an axisymmetric potential from this whole data set. But at the same time, I think the automatic way with with machine learning may be interesting in the sense that it essentially has no, well, it has a different set of assumptions. And on some level, it's agnostic about what the Hamiltonian is.
Well, it will be very interesting to know the results.
It may take a little while. Yeah. So I have a question for you. Is there somebody in this group who's working on tabular type data? Or are most people interested in imaging, in images, in image analysis?
Well, I think currently in the Minerva project, most of the people are working on images, but I have personally worked a lot on tabular data, so I think we can discuss at least the two of us. Maybe some other have done similar things. Maybe Aristide, I don't see him in the participant right now, but I think he have made some work on tabular data as well. And I think we have another question, David.
Yes, thank you. Thank you, Rodrigo, for a brilliant talk as usual. I'm a bit concerned, a little bit like Françoise, on the accuracy of the final accelerations that one will get. As James Binet famously said, I mean, galaxies like elephants have long memories, right? And so in a potential which is changing with time, I'm not quite sure whether you have really redundant information when along a line of sight, you will have several streams crisscrossing, because they are actually sensitive to potentials at different times. So, so have you looked at this a little bit with simulations, perhaps, with that time varying potential?
No, we haven't, and it's something that we have to do. I mean, really, for the time being, what we've done is essentially a proof of concept that one can do this, right? And so it took quite a bit of effort to get the algorithm up to its present state. But you're completely right. I mean, as things like the LMC come in, as the galaxy adapts itself. I mean, at some level, these are the right coordinates to be looking at the galaxy in, precisely because of the adiabatic invariance, right? But you're right, of course, that things will change over time, and maybe for some of these, some of these were formed, some of these streams were formed when the galaxy looked quite different. I mean, there's a guy, oh no, it's in the other plot actually. This little guy down here, for instance, is a, probably one of the very first structures that formed in the Milky Way. I mean, has the lowest metallicity. So yes, almost certainly they will have probed a different potential over that time. But currently they do, these structures still do appear stream-like. So at some level they've retained their coherence, and they're currently orbiting in the present day potential, obviously, right? So I don't expect that we'll get too many surprises, but we'll see. But you're completely right. I mean, we need to do this. We need to run a proper simulation and with at high resolution in which we can form these globular cluster streams and have a Milky Way that is live. I mean, this is very, it's technically quite challenging as well, right?
Well, yes, definitely. I mean, what we've done is really a tour de force, right? So it's really impressive. But I feel that reality will be a bit more complex.
No, it may well be. No, indeed, it may well be.
Thanks.
Thanks, David.
Benoit, you wanted to add something? I see your mic open.
No, not really. I think I feel I'm not familiar enough with this astrophysical problem to be able to really comment or ask questions, unfortunately.
Okay, I think, Jonathan, you have a question as well.
Yes, I had a very small question, but more to better understand, which is that now your algorithm has one of the main assumptions is that J should be constant for a given stream. But in case, like this is a bit following François and David's concerns, if J is not exactly constant, do you think it would be easy to change this condition of J equals constant to J being a slowly varying function, or some function that is relatively regular along a stream with some derivative conditions? And would this be possible?
So kind of what I was hoping to do, and that we kind of begun doing, right, is running, I mean, we have libraries of, for instance, of the formation of this particular system here, for instance, this PAL5, right? You know where the remnant globular cluster is. You have a stream on the sky. You know roughly what the potential is, as François was saying, and that gives you then essentially a correction function between a given potential and the track on the sky. And you can do in exactly the same way. You can correct also the again, assuming that this potential is roughly right. You have a correction then for the actions that you'd find in this particular system. And so the way that I had in mind to actually apply this to real data was essentially that. Essentially, each one of these structures, and as we were seeing, there are quite a few of them, will probably require an n-body simulation to properly model, and hopefully, the differences between different potentials won't be huge to the point that you don't need to run an n-body model in every possible potential that you want to analyze, but one that's near enough will do. And then you just apply the same corrections, be it in position and velocity or action and angles, to the data set here, so that when you actually come to fit each one saying, the actions are constant along this structure here, perhaps, you're actually doing that with the correction thanks to an n-body model. So that's the way that I see this being done perhaps in something like a year's time. But it's quite a lot of effort, obviously, to get good models that fit each one of these. And in many cases, we have no idea where the progenitor is, right? There's like, yeah, so maybe like 10 of these have known progenitors, but the rest are, the progenitor has disappeared. And so there's quite a lot of uncertainty as to, where the progenitor would have been, and hence how you actually properly correct the tracks.
Okay, is there any other question for Rodrigo? I have one actually, so I'm sorry if you already said that in your presentation, because I had quite a lot of connection issues on my side, but do you have any estimation of the uncertainty of your network prediction, like a posterior probability distribution, for example?
Yeah, so essentially the way that we've been trying to see, its accuracy is by assuming that the going the wrong way. It's essentially using this method developed by James Binney called the torus machine. So we use this method as it's implemented in a software called a Gamma. And so we're using this as kind of the ground truth for a particular model. And what we're doing then is trying to do the opposite. And what we're finding is that with less than about 1,000 data points, we're able to, so essentially something like, if we had 100 odd streams, each with 10 stars along them, that would be enough to do at least as well as this particular algorithm here. And we were able to recover the actions that are input into this algorithm here to better than 1%. I don't know if that really answers your question.
Kind of. I would have maybe some suggestions or things we can discuss afterward.
So one of the problems that kind of surprised me is that it's that there's well, there seems to be a plateau in the and I don't know actually where it's coming from. I mean, the problem is that it's actually quite difficult to get the ground truth for systems of interest. So apart from the toy isochrone model and also the Steckel model, there's no other system that's known that allows you to get the actions and angles analytically, and so one has to use some algorithm like this, and I think these also have their limitations, right? I mean, this is limited to by the Fourier decomposition, and may well have similar sort of accuracy to our method. One thing I didn't mention is that in our network is fully invertible, so we can go both ways in this particular in this coordinate transformation.
Mm-hmm. Okay, thanks. So I think we may be finishing here because already a lot of people have left the meeting already. So thank you, Rodrigo. Thank you very much.
Yeah, thank you very much.
If you want to stay a few minutes, maybe some of the Minerva members will stay as well, but I think we will close this seminar right now. So thank you everybody for attending, and we will see you next week for a talk by Antoine Marchal, which will talk about his software ROSA to reconstruct H1 structures of the ISM. So thank you everybody, and see you next week.
Thank you very much.